Good morning, class. Welcome to the fifth lecture video of ME269, Material Science and Engineering. So in this video, I will be discussing the failure of engineering materials. So let's get started. So why study failure? So the design of a component or structure often calls upon the engineer to minimize the possibility of failure. So every time na nagde-design ng isang mechanical engineer, laging tinitake into consideration the failure part of the material, no? Kasi lagi nating iniiwasan 'yan. Thus, it is important to understand the mechanics of various failure modes such as yung modes of failure natin, we have three kinds. So they are first, fracture, fatigue, and creep. So all throughout ng video natin, i-discuss natin tong tatlong 'yan. So in order for us to understand more the importance of failure, so magbibigay ako ng mga incident where nagkaroon ng failure sa materials. So we have here Aloha Airlines Flight 243. Kung makikita nyo, yung body construction of the airplane, nasira na siya, or the fuselage. So it was a scheduled Aloha flight between Hilo and Honolulu in Hawaii. So on April 28, 1988, suffered extensive damage, as you can see here. So failure was attributed to fatigue fracture of the panels forming the fuselage in the section weakened by rivets. So hindi na take into consideration, no, na kasi usually ang connection ng body panels ng aircraft vehicle lalo na dati is not by weldment. Ang gamit dito is by rivet. Due to the fatigue fracture, siguro pa ulit-ulit na pressure na tinatanggap ng body construction, lalo na yung maliit na rivet. So that is the reason why it got destroyed. So ganun ka-importante, no? Sobrang liit lang na part ng machine natin, if it undergo a certain kind of stress, it may turn into failure. So baka magkaroon pa to ng mas malaking damage dun sa machine natin. Next, Space Shuttle disaster or the Space Shuttle Challenger. So it took place on January 28, 1996 when the shuttle broke apart precisely 73 seconds into flight. So it was found that the space shuttle's external fuel containment had collapsed, which released all the liquid hydrogen and liquid oxygen propellants. So yung fuel containment na to, it is a pressure vessel wherein siguro hindi na take into consideration the amount of pressure inside the fuel containment. So hindi kinayanan yun ng pressure vessel yung pressure na yun. Therefore, it leads to the material failure and therefore a bigger accident. So ganun ka-importante yung failure ng material. Last, Sked plane disaster of 1998. So on June 3, 1998, near the village of Sked, Germany, a high-speed train derailed and crashed into a road bridge. So 101 people were killed and 88 were injured. So the reason behind this, so the cause was a single fatigue crack in one wheel. So ganun lang kaliit, no? Yung reason wherein nagkaroon ka ng malaking outcome. So ganun ka-importante yung pag-aaral ng failure ng material. So first, pag-usapan natin yung fracture of the material. So fracture, it is the separation of a body in two or more pieces in response to an imposed static stress and at temperature that are low relative to the melting temperature of the material. So ito yung pangkaraniwan na nangyayari dun sa ating material kapag nagkaroon ka ng static stress. So for example nito is the material testing natin. So tawag dun sa pagkasira nung tinetest nating material in material testing or the destructive test natin, that is called fracture. Kasi yung nilalagay nating force or the stress that took upon to the material is considered as static stress. In addition, yung nabanggit dito na low relative to the melting temperature of the material, because if the material has a temperature near its melting point, it changes the mechanical property. So pag sinabi nating low relative, it can be considered as a normal temperature, no? So any fracture process involves two steps in response to an imposed stress. So they are first, crack formation, and lastly, the crack propagation. So in layman's term, pamumuo ng defects and paglaki ng defect. So for engineering materials, two fracture modes are possible. So they can be ductile fracture or brittle fracture. So first, let's discuss the ductile failure. So, as you can see in the figure, kapag ganito yung nangyari dun sa ating specimen, highly ductile fracture in which specimen next point down to a point. So, halos perfect yung pagka fracture ng ating material to a point na kakatuldok lang yung separation nila. So, pag highly ductile yung fracture natin, ganyan ang itsura. So, fracture is preceded by only a moderate amount of necking. So, kapag moderate amount of necking lang yan, so, ano to, can be considered a ductile material pa rin, pero hindi na to a point na highly ductile material. So, it is considered as ductile material because of course, we have a necking here. Pero hindi rin siya ganun ka-visible. And lastly, if we have a brittle fracture, makikita mo wala kang any form of plastic deformation. So clean break ka. Hindi kagaya ng mga ductile material talaga na nagkakaroon ka ng necking. Dito, clean break. So in ductile failure, ganito ang nangyayari. If the specimen is undergoing a tensile stress or the pulling stress, so nangyayari kapag ductile, nagkakaroon ka ng visible necking. So kapag nagkakaroon ka ng necking, you are approaching the ultimate stress or nakapunta ka na or na-reach na ng material natin yung ultimate stress. After that, small cavities form in the interior of the cross-section. So, nangyayari dyan is yung grains na ng material natin, nagkakaroon ka na ng gaps inside. So, hindi siya visible, of course, kapag pinag-aaralan mo siya. So, because the cracks or the cavities form to the interior of the cross-sectional area. So, nangyari dyan, the bonds between the atom of our alloys or any material na nawawala na or nasisira. After that, those cavities enlarge, come together, and coalesce to form an elliptical crack. So, ang nangyayari bale is namuo yung mga small cavities initially, no? And then it forms in large elliptical crack to the interior of the cross-section. Finally, fracture ensues the rapid propagation of a crack around the outer perimeter of the neck. So, napansin nyo, meron ditong sinabi na rapid propagation for the reason that the stress magnified kapag nagkakaroon ka ng cracks inside the material. So, mamaya i-discuss natin yung tinatawag nating stress concentration wherein stress can be magnified or nagfo-focus siya, no, or lumalaki value niya at a certain point ng material natin wherein mahina yung material. So, in this case, yung mga crack formations natin. So, what will happen is here, kapag nasira siya, makikita mo na visible yung fibrous part. Kasi hindi kagaya nung kanina pinakita natin kapag very ductile yung material, certain point lang yung division nila. So sometimes this fracture surface is termed as cup and cone fracture. Parang ganito. Due to the shape na nabuo. So parang cup, ito naman is parang cone. So the central interior region of the surface has an irregular and fibrous appearance which is indicative of plastic deformation. Kapag brittle material ka, hindi ganyan ang itsura. Next, let's talk about brittle failure. So, it takes place without any appreciable deformation and by rapid crack propagation. So, hindi siya kagaya nung kanina wherein matagal bago magkaroon ka ng pagkasira, no? Kasi nagkakaroon ka pa ng deformation or the necking natin. In here, rectang rapid crack propagation kagad at magkakaroon ka ng clean break parang ganito. Hindi rin siya ganun ka-fibrous kagaya nung kanina. So the direction of the crack motion is very nearly perpendicular to the direction of the applied tensile stress and yields a relatively flat fracture surface, just like this. So fracture surface sa material that failed in a brittle manner will have their own distinctive patterns. So hindi kagaya ng mga ductile materials natin na pangkaraniwan na shape nila or geometry once it undergoes fracture is cup and cone. In brittle failure natin, the pattern occurs depending on the material itself. So first, we have these V-shaped chevron markings. Nakadepende kasi sa material yan. And we have here a radial fan-shaped ridges. So next, let's talk about stress concentration. Ito yung nabanggit ko kanina, no? Wherein the stress will magnified once the crack formed inside the material. So kunyari, we applied a certain stress to the specimen, and then the specimen has a certain fracture inside the or the defect inside the cross-sectional area. Yung stress na napupunta dun sa defects natin is mas malaki dun sa ina-apply mong stress. So that is called the stress concentration. So measured fraction strength for most brittle material are significantly lower than those predicted by theoretical calculations. So this is due to the presence of microscopic flaws that always exist under normal condition at the surface and within the interior of the body of material. So specifically ito sa mga metals natin wherein the construction or pagka-fabricate ng material natin is hindi perfect. So sa loob nung alloys natin, steel alloys natin, meron yung gaps inside wherein it can lead to stress concentration. So ganito itsura niyan sa loob pag meron kang gaps. So first, we have this vacancy that is also considered as a defect and it can be interstitial. Pag sinabi natin interstitial is the atom of the alloying element nakapatong doon sa ating other atoms. Ulitin ko, it can be vacancy, may kulang, or nakapatong, or the interstitial. So for example, we have this test material and it undergoes a normal tensile stress. Pahila, no? Yung pwersa natin. And then, yung material natin, merong crack sa loob. So, yun yung crack natin. So, the size of that crack will be 2A. Mamaya kasi may equation for stress concentration. So, let's say that the material is equal to 2A. Bakit 2A? Because the size of a normal crack or surface crack is considered as A. Kasi pag surface crack ka, half ellipse ka lang. Kapag interior cracks, it has a shape of a full ellipse. So kapag surface cracks meron, A tawag natin dyan. 2A naman kapag interior cracks. So if we zoom in those cracks, yung curvature or the radius of curvature natin for the side ends ng ating ellipse, it can be measured by this rho sign, rho t. So pag tinignan natin yan, we have this stress and position graph. So ang y-axis natin will be the stress and yung x-axis natin will be the position along x dash x prime. Ito yan. So itong x, small x and x prime natin, that will be the position of our crack. So for example, meron tayong stress na in-apply which is yung omega 0 natin or the initial stress. Pinlat natin yan. Pero palapit ka ng palapit doon sa ating location ng ating stop, makikita nyo na yung stress natin is lumalaki. So therefore, it undergoes a stress concentration. Ibig sabihin, kapag meron kang interior cracks or any form of crack, palaki ng palaki yung stress mo. So that is equivalent to OM or the O maximum. So due to their ability to amplify an applied stress in their local, these flaws are sometimes called stress racers. So yung mga flaws natin or the cracks inside or outside the material, tinatawag din natin yung stress racers. So maximum stress or the OM, yung natatanggap ng ating crack. Yung OM nga pala natin yun dun sa sa position na to, sa end ng ating ellipse. So it can be quantified or measured using this formula. So ang formula natin for the maximum stress is 2 multiplied by the applied stress, omega 0, yung nilagay mong stress, multiply by A. A is the half size of the ellipse, no? All over rho t or the radius of curvature ng ating crack raised to 1/2. So sometimes the ratio of the maximum stress and the applied stress is denoted as the stress concentration factor or KT. So OM all over applied stress, which is equal to 2 multiplied by the size of our half ellipse all over rho or the radius of curvature of our defect raised to 1/2. So it is simply a measure of the degree to which an external stress is amplified at the tip of the crack. So the effect of a stress racer is more significant in brittle than in ductile materials. So in ductile material, the stress is distributed more uniform of in the stress racer and the maximum stress concentration factor less than the theoretical value. So kapag ductile material daw, the value of the maximum stress concentration factor here is less than the maximum theoretical value or the critical value of the stress. So hindi siya ganun kagad masisira as long as the maximum stress doesn't reach. So hindi yan kagaya nung brittle material. Since these do not occur in brittle materials, theoretical stress concentration will result. So in brittle material, lagi nating kino-compute or kina-calculate the theoretical stress concentration. Kasi iniiwasan yan. Kapag ang value na na-compute natin for the maximum stress concentration is larger than the theoretical one, what will happen is that the cracks so kapag ang value ng maximum stress concentration natin is larger than the computed theoretical stress concentration, what will happen is the defect or the gap inside the material will propagate or lalaki until it reach failure. So in calculation for the theoretical stress natin or tinatawag din nating critical stress, kino-compute yan. So critical stress required for crack propagation in a brittle material is described by the expression here. So omega C or the stress critical, which is equal to quantity 2E gamma S all over pi A raised to 1 half. So ang E natin will be the modulus of elasticity of the material. Gamma S will be the specific surface energy. A will be the 1 half length of an internal crack. So when the maximum stress at the tip of one stress razor exceeds the value of the critical stress, a crack forms and then propagates, which results in fracture. So itong formula natin na to, ginagamit lang natin yan for brittle material. So let's have a sample problem para mas madali nating magets yung binigay nating equation. So a relatively large plate of a glass is subjected to a tensile stress of 40 megapascal. If the specific surface energy and modulus of elasticity of this glass are 0.3 joules per meter squared and 69 gigapascal respectively, determine the maximum length of a surface flow that is possible without fracture. So ang solution natin dun sa ating problem, ang formula na gagamitin natin is the stress critical because it is very obvious the material na ginamit natin is a plate of glass, therefore it is brittle. And then, hinahanap kasi natin yung maximum length of the surface that is possible without fracture. So, that should be the stress dapat na critical na pinag-uusapan. So, isolating letter A, which is the maximum length of surface flow. Kasi if it is internal cracks, it should be 2A. Pero since hinahanap lang naman natin is the surface flow, that would be A. So it is equal to this. So ang E natin will be 69 times 10 raised to 9 because we have 69 GPa as the modulus of elasticity. And then we have specific surface energy with a value of 0.3 joule per meter squared. In this case, ang value na unit natin will be Newton per meter. Because joule per meter squared, joule is equal to Newton per meter, makakancel yung meter na isa dun sa baba. Kaya magiging Newton per meter. And then the value of our omega or the stress will be the 40 megapascal. So that will be 40 times 10 raised to 6. So the value of our maximum length of surface flow will be 8.2 times 10 raised to negative 6 meter or 8.2 micrometer. Next, let's talk about fatigue naman. So fatigue, it is a form of failure that occurs in structures subjected to dynamic and fluctuating stresses. Hindi kagaya nung fracture natin. Kasi sa fracture, ang ating loadings or stresses natin is static, no? So hindi pa bago-bago. So in fatigue, yung stress na ina-apply natin doon sa material natin will be dynamic and fluctuating o pabago-bago. So this is the example of our material that undergoes a fatigue. So kung makikita mo yung grains niya doon sa ating failure is different with the other. So makikita nyo, itong part na to, which is the origin, dyan nagsimula yung crack propagation due to fatigue. And if that propagates, makikita mo, it will undergo the fatigue zone. And this part, yung makinis na part, that will be the final failure. So under these circumstances, it is possible for failure to occur at a stress level considerably lower than the tensile or yield strength for a static load. So for example, we have a certain material that has a ultimate strength. So, kayang mag-fail ng material na yun kahit hindi niya nare-reach yung ultimate stress na yun. Because if it undergoes fatigue, it can also lead with the failure of the material. So as you can see, the material here is like brittle-like in nature. Kahit ductile yung material mo, or brittle or ductile man niya, the image or the surface na nangyayari will be like brittle-like. So, hindi mo makikita kagaya ng ductile na nag-undergo ng static load. Meron kang fibrous surface. Dito, hindi. So, in fatigue, let's talk about cyclic stresses. Kasi hindi nga siya linear or static, no? The stresses here are cyclic. So, the applied stress may be axial, flexural, or torsional in nature. So, first, we have the stress time diagram because cyclic nga siya, no? So, yung stress natin, lagi siyang in terms of time. So, we have here the maximum stress and the minimum stress. Yung max natin, that is possible positive value, and the minimum stress natin will be negative value. And kapag tensile stress tayo, or yung tensile stress yung nag-undergo do sa material natin, that is positive. Pag compression, negative. So kapag ang nangyayari dyan is if we have cyclic stress and equal yung tensile force natin dun sa compressive force, maximum tensile force sa maximum compressive force, that is considered as reverse stress cycle. Next, if the maximum tensile force or tensile stress of the material is larger compared to the maximum compressive stress, this is called repeated stress cycle. And lastly, we have this random stress cycle. Hindi siya kagaya nung naunang dalawa wherein meron tayong certain patterns for the tensile and compressive values natin. So usually nagkakaroon ng ganito kapag under vibration, no, na hindi equal o random yung cyclic stresses natin. Yung sa naunang dalawa, possible siya sa mga rotating bodies. Next, let's talk about different terminologies on our cyclic stresses. So first, we have this mean stress. So the stress amplitude alternate about a mean stress, OMN, which is defined by the sum of the maximum and the minimum stress divided by 2. So average ng dalawa. So maximum, the maximum value of tensile stress, and O-min will be the maximum value of our compression stress. So negative yan, ha? And then, i-divide natin sa 2. Ito yan, OMN. Range naman is defined as the difference between the maximum and the minimum. So, ito yung OR natin. Stress amplitude, OA, is defined by OR divided by 2. Or the difference between Omax and Omin divided by 2. Ito ang ating omega A. So for the stress ratio naman, that will be equal to the ratio between the minimum stress and the maximum stress. Let's talk about fatigue test and SN curve. So yung fatigue test, this is an example of destructive testing of a material, no? So kung mapapansin nyo, hindi siya na-discuss from the previous topic of material testing because hindi pa natin na-discuss yung fatigue natin or the definition of the fatigue. So in this case, kasama natin sa lecture natin yung common setup ng fatigue test. So for the schematic diagram of fatigue test, first we have this motor. It is coupled with counter wherein pinakount ng ating counter yung rotation or the cycle of our motor. Connected yan with a flexible coupling kasi ano mami-misalign yan mamaya kapag wala kang flexible coupling. And then that is connected with two support bearings. And between those support bearings, we have load bearings. So dito nilalagay yung load. And in between those load bearings, meron tayong specimen na pinag-aaralan. So yung specimen, ito yung tinetest natin ng fatigue. So in load bearings, meron tayong specific load. Typically, by weights yan. Merong hanger yan, tapos nilalagyan ng weights. Pero in some setup, meron yang power screw na hina-hand wheel or minomove wherein the force applied is measured by a spring scale. So nakadepende yan dun sa setup. So in this case, we have this load. So what will happen kapag nilagyan natin ng load is magkakaroon siya ng bending. And then continuing the rotation of the motor, pinapaikot niya yung specimen natin kahit meron siyang load. Kaya meron yung flexible coupling kasi kapag nilagyan natin ng load yan, mami-misalign yung shafting natin. So parang ganito ang nangyari. Medyo ano lang, no? Medyo exage lang masyado yung pagka-bend. Pero parang ganito yung mangyayari. Magkakaroon ka ng bending. So in bending kasi, the other half of our material will have tensile. Pahila naman talaga yung grains yan, di ba? Pag binali mo, pahila yan. So tensile nangyayari. And then the inner part or the other half of the specimen will undergo compressive. So each part of the material has tensile and compressive forces. And imagine we have we are rotating the motor. Patuloy yan, no? Tapos meron kang compressive and tensile force. So ibig sabihin, alternating yung compressive and tensile mo. Therefore, it will have a cyclic stress. So ganun yung nangyari. Combination ka ng tensile and compressive stress at a certain cycle. So next, let's describe the SN curve. Yung SN curve yung ginagamit para maintindihan or ma-visualize ng maigi yung fatigue test values natin. So in SN curve, the end part, di ba SN nga siya, yung end part that will be the number of cycles to failure. So for the y-axis naman, the S part, that will be the fatigue stress. So the amount of stress that is applied to the material. So kapag tinest mo yung material natin, kung makikita mo, ang ating data na makukuha is hindi linear. So in order for us to understand more the values here, gumagamit tayo ng logarithmic function para ma-convert natin yung values natin into linear manner. Kasi kapag ganito, yung dots natin kanina, mahirap talaga maintindihan niya or i-interpret. Kasi wala kang certain pattern, no? Or masyadong random yung values. So for example, the material natin undergoes a 150 megapascal fatigue stress. So kapag nilagyan mo siya ng 150 megapascal of stress, you will project it pababa. So the value na mababasa natin, which is in between 10 raised to 5 and 10 raised to 6, that will be 500,000 cycles to failure. So para pag nag-apply ka ng 150 megapascal, kapag na-reach mo yung 500,000 cycles, mag-lead yun sa failure. So ganun yung interpretation. So ang tawag natin dito sa 500,000 cycles, that is the fatigue life ng material. So kapag continuing ka na nag-a-apply ng 150 megapascal to a certain material, if you reach a certain cycle of 500,000 cycles, yun lang yung life niya bago siya masira. So, kunyari we have 1 cycle per minute, no? So Pag kinumpute natin yon, that will approximately 1 year to failure. For example, the cycle nga natin na ina-apply is 1 cycle per minute. The approximation natin bago siya masira will be the 1 year. So ito yung fatigue life talaga. Fatigue life ng material. So ang tawag naman natin dito, kung makikita nyo, hindi siya continuing na bumaba. No? Hindi siya tuloy-tuloy na pababa. At a certain point, dumiretso siya horizontally. So ang tawag natin doon is the endurance limit. So yung stress below the endurance limit is the safe zone for the material. So kahit gaano katagal or kung gaano karami man cycles yung i-apply mo dun sa material mo, hindi siya masisira. Pero once na lumagpas ka doon sa endurance limit, may limitations na material mo. Meron na yung fatigue limit. Fatigue life. So that will become the infinite fatigue life. Hindi yan masisira. So it is only possible kapag ang material mo is ferrous. Kapag ferrous ang material, meron kang infinite fatigue life. Pero kapag ang material mo is non-ferrous, such as aluminum, copper, etc., ang material mo will break due to fatigue stress kahit gaano kababa yung stress mo. No? Kahit sobrang liit na stress i-apply mo at a certain number of cycles, masisira at masisira ang non-ferrous material. So yun yung pinagkaiba ng ferrous and non-ferrous. Kaya ang mga ferrous material, they have a large amount of fatigue strength compared to non-ferrous. Next, let's talk about high cycle and low cycle fatigue. So if we draw an imaginary line here, so lahat ng stresses that proceeds in this side of our graph, that is called high cycle fatigue, no? Because kailangan mo ng maraming cycle before ka magkaroon ng failure. Ang tawag naman natin dito sa part na to is low cycle fatigue. Because konting cycle lang ang kailangan mo bago masira. And if we are undergoing the high cycle fatigue, nag-undergo ang material natin ng elastic deformation. And if the material is undergoing a low cycle fatigue, the material will follow a plastic deformation kagad. So let's discuss the crack initiation and propagation in terms of fatigue. So if we are rotating the specimen with with a load that is static here, so magkakaroon ka ng cyclic load, no? Kagaya nung sa fatigue test natin. So what will happen is magkakaroon ka ng crack initiation dun sa loob. If continuing pa rin yung ating dynamic load here, and then the cycle also continues, patagal na patagal, that crack will propagate. And eventually, it will lead to failure just like this. So factors that affect fatigue life are, first, the design factor. So laging kino-consider yan ng isang designer o ng isang mechanical engineer. So any geometrical discontinuity can act as a stress raiser. So for example, naglagay ka ng notch, no? Or ng other deformation or uka dun sa ating material, it will lead to or it will increase the fatigue limit of the material. So ano ba yung mga design features na yon? So kagaya na banggit ko, notch, grooves, holes, pag may butas, no, na nagiging stress raiser yan. Mga keyways sa gears, no? Sa gears natin, usually may keyway yan kasi nilalagyan ng key. That is the reason why sa mga gear ko napapansin nyo na medyo embossed yung or naka-umbok yung part na or mas makapal yung part na merong keyway in order for the gear natin na increase the strength. So next, the thread, of course, that is also a stress raiser. So usually sa design natin, nakakatulong din kapag naglalagay tayo ng fillet. So that fillet will distribute the loadings that will help the shafting natin. Usually kasi shafting to ginagamit, no? At madagdagan pa yung fatigue life niya. Next, surface treatment. So, ano ba yung mga surface treatment example? First, shot peening, which is an example of cold treatment. Shot peening, pinapatigas mo yung surface ng material para tumaas yung fatigue life niya. So, ito example ng shot peening. So, nagbo-blow ka ng small pieces of balls dun sa ating piece metal and then parang hinahammered niya yung surface until tumigas. So yung surface mo has a different hardness compared the interior or the interior part of our alloy or material. So makikita nyo, this is the fatigue or cycles to failure ng normal. Mas mataas yung sa shot pin. No? Next, case hardening or an example of hot treatment. So, sa case hardening, ginagawa mo is carburization ng surface metal. So, ginagawa mo is ini-increase mo yung temperature at the surface, tapos nilalagyan mo siya ng carbon usually. What will happen is the surface will hardens. So, what are the fatigues due to the environmental conditions? So, we can consider thermal stresses as the reason for thermal fatigue. So, thermal fatigue is normally induced at elevated temperatures by fluctuating thermal stresses. So, ang formula natin for thermal stress is equal to alpha E delta T. Ang alpha natin will be the coefficient of thermal expansion, E natin will be the modulus of elasticity, and delta T natin is the temperature difference. So, kung pabago-bago yung ating thermal stress with the material, so for example, nasa environment ka wherein ginagamit mo siya at hot condition, tapos pag hindi mo siya ginamit, nagiging cold condition siya. If that will happen, the thermal stress will fluctuate, therefore it will act as like dynamic loading. So magkakaroon ka rin ng fatigue doon. Next, we have corrosion fatigue, which occurs by simultaneous action of cyclic stress and chemical attack. So nahihina yung integrity ng ating material dahil sa corrosion. Lastly, let's talk about creep. Creep Creep is the deformation when a material is placed in service at elevated temperatures and exposed to constant mechanical stresses. So, nangyayari siya kapag elevated yung temperatures natin. So, in comparison dun sa una natin, which is yung failure, ang failure natin kasi kapag ang temperature is malayo sa melting point, meaning that will be the normal temperature or below the normal temperature. So, ang creep nangyayari yan kapag elevated, masyado mataas yung temperature natin. Example niyan is turbine rotors. Of course, turbine rotors works on elevated temperatures because steam yung dumadaloy sa kanya usually. And then the mechanical stress is also constant because of the pressure exerted by the steam. Next, we also have steam generators. No? Pressure vessels yan. And of course, the temperature in that condition is very high because it operates on steam. And then the pressure inside also gives of constant mechanical stresses. Also same with the high pressure steam lines. So this deformation is permanent and time dependent. So the creep behavior is like this. So compared kanina, no, sa in comparison lang dun sa ating fatigue, that is also time dependent, but the y value natin sa graph kanina is stress in terms of compressive and tensile. Dito naman, ang y value natin for our graph will be the creep strain or yung pag-deform ng ating material. Epsilon yan. So for the first part of our creep behavior, tawag natin dyan is the primary. Primary or transient creep. So that is continuously decreasing creep with time. So ibig sabihin yung integrity ng material mo is continuously increasing or decreasing due to time. So the material is experiencing an increase in creep resistance or strain hardening. Because of the grains inside of the material, ang nangyayari, tumitigas din yung material mo. Kaya kung makikita mo, the graph, naging straight yung ating itsura compared dun sa initially na curvature natin. Because due to the change on the mechanical property of the material, since tumigas siya, hindi na continuous yung paglaki niya or pa-curvature, naging straight siya. So ang tawag natin dito ay secondary creep or sometimes called steady state creep. Bakit siya tinawag na steady state creep? Because the motion of our graph will be linear. Pag linear yan, meaning the epsilon natin, change in epsilon, is equivalent to the change of T natin. Or it has a linear relationship. So the rate is constant and it has the longest duration. So after some time, pag patapos ka na sa secondary creep, what will happen is the material becomes softer and retains its ability to experience deformation. So magkakaroon ka ulit ng curvature. So ang tawag naman natin dyan is tertiary creep. So tertiary creep is from secondary creep up to the rupture of the material. So there is an acceleration of the rate and ultimate failure. So parang nangyayari, primary, malaki yung deformation natin na nangyayari. Babagal siya dun sa ating secondary creep due to strain hardening. And then after it reaches final stage of secondary creep, the material will lose its integrity and it becomes softer until it goes the tertiary creep. Tapos mag-accelerate na yung rate niya due to failure. So this failure is frequently termed as rupture and results from microstructural changes. So that will be the end of the lecture. If you have any questions, you can message me on my messenger or email me. Thank you.
Fire.
Emmy, faculty, yeah. Emmy, faculty, yeah. Emmy, faculty, yeah. Emmy, faculty. Siya naman si Sir Ivan Espinosa, dulo ng pangalan. Pangako di mahihirapan at hindi kanya iiwan.